Okay, welcome back, everybody. So we're happy to have Julia Plavnik, who will tell us about comparing different constructions of modular categories.
Yeah, thank you so much for the invitation, Josh, and for the introduction. And as you can see, my handwriting is not really great, so please stop me at any time if you don't understand what I wrote or what I said, and also if you have any questions. So yeah, the idea of the talk is that I will start introducing these categories, which are highly structured categories, and that are kind of the main focus of my research, studying these objects. And this talk is based on two different projects, two different constructions, actually, one with my colleagues Sean Sui, Cesar Galindo, and Shenhan Wang, and the other with Colin Deligne, Cesar Galindo, Eric Rowell, and Ching Sang. So before giving the formal definition, I would like to tell you a little bit why I study these modular tensor categories, why I really like them. And I enjoy a lot studying these objects because they appear in very different, or in many different areas of math. So you can see that they are connected, or that you can approach them from more like an analysis point of view if you study von Neumann algebras, if you study subfactors, planar algebras, or you could approach them more from a topological side. So if you're interested in low dimensional topology, in knots and links invariants, if you're interested in TQFT, there are connections in that way. They are connected to other topics in algebra and physics, quantum groups, Hopf algebras. This is how I came to this world of modular categories, CFT, vertex operator algebras. And also, they are very exciting because a lot of physicists care about them. They appear, or they are useful to model some topological phases of matter. And because of that, they are useful for topological quantum computation, or in principle, they might be useful for topological quantum computation. Let's say more like it might, but that's kind of the idea. And the other thing is that, or related, or why they appear in so many places, maybe I should erase the modular here, but like groups are natural hosts for symmetries. But in a lot of these quantum contexts, now groups are not longer enough to describe the symmetries of some quantum objects. And the natural or the unifying language to describe that symmetries are tensor categories. And modular tensor categories are a special class that I will focus a little bit more on. So that's why I am excited about this topic. And maybe let me tell you a couple of words before I start with the definitions, but this is a very young theory. So we really need to develop a lot of things. You should think that we are like in the very early stages. So for example, we are in look of more examples. We don't have that many examples, and I will tell you the main sources of examples in a couple of minutes. And there are different problems that people think about. I'm specifically interested in classification problems. I also like a lot studying invariants and some properties of these categories. And the one that I will focus today is constructions. So one thing that I have fun doing is you give me one modular category or a fusion category or a tensor category, and I would like to try to construct a new one out of that one. Probably one of the motivations for this is also understanding these others, and they are all connected. They are all connected. They sometimes classifying, you get ideas for this, or when you're trying to study invariants, they are useful and appear in the classification. So they are all connected. So I want to give a definition. I will start giving this definition by an example. And as a disclaimer, this is not really a definition of a modular category. We will go first to a braided fusion category. And later I will tell you why this is not modular and what are we missing. And we will give a concrete definition after this. So the category that I want to look at, it's the category of representations or finite dimensional representations of a group G. And here for me, G will be a finite group. And here I don't need to have complex. I'm taking complex. You can do it more generally, but it will be easier to do complex for now. If we don't do complex, we lose some of the properties. They are still interested. They are still tensor categories. But I will fix the field to be complex or characteristics even algebraically close for this talk. So what are the nice things or some of the nice things that I like about this category? So I didn't say, but the home spaces are the intertwiners. So we have objects, these finite dimensional representations, and the home space are just the maps between these representations, the maps that preserve the action. So what I like about this is if you give me two of these representations, I can give you a new one by taking the tensor product. And here we will act just by the diagonal action. So as you see, I'm kind of using actions and modules instead of representations directly, but I'm doing, so this is the diagonal action. Other nice thing is we have a distinguished representation that it's just a field, and here we'll consider the trivial action. And it's nice for many things, but one of the things that make this nice is that now if I do this using C as P, for example, this will be just isomorphic to W. So it's kind of a unit for my tensor product. The other thing that I like is that if you give me a representation, I can give you a new one looking at the to the linear dual. So I look at the linear to the dual vector space of this, and I can endow this with an action. So how I will act using that I can act on B with G, but instead of acting with this G, I will act with the inverse. So this is the contra gradient action. And then Maschke theorem tells me that every representation is completely reducible, so I can write any. Okay, here I probably wrote something. So I can write any representation as a sum of irreducible ones, as a finite sum of irreducible ones. And other thing that I like is that I have this flip of the representations, just swapping the factors, but this is a map in this category. Other nice thing is that G is finite, so I have only finitely many of the irreducible representations. So these are all the nice things that I have seen. And all these are the things that we look when we want to talk about braided diffusion categories. So now let me tell you what a modular category is, and I will tell you where rep G breaks, basically, or what it's a braided diffusion category from all these. So the first thing that I want to have a modular category is an abelian structure of my category. So I will want to have a direct sum, I want to have kernel, co-kernels for the morphisms, a zero object. And the other thing that I need, and that's why it's important, the field, is that my category is C-linear. So, or it's linear with respect to some field. Here we are picking the complex. So what I'm saying is that the home spaces in my category are not just sets, these are C vector spaces. Okay. So the other thing that I want, that it's the one related to Maschke's theorem, is that, and this is just something that we care in the, like in this abelian structure, we want that all objects can be written as a finite direct sum of simples. So we will basically be looking a lot to these simple objects, because then all the other things are like we can look at all of them by extending by linearity. Basically, we have these direct sums. Other thing that I will add to this semi-simple abelian category is to be finite. And here I will cheat a little bit, since I already asked for semi-simple. I will not say all the really required things. It's easier because we already have semi-simple. So one of the things that I need here is to have finitely many simples up to isomorphisms. So I will only have a finite number of these simple blocks that I use to construct all the others. And then the other is, here we have these vector spaces. I will ask that these vector spaces are finite dimensional. So as you see, we have a lot of finiteness conditions here. Now I will add more structures. So we add first this structure, and then we ask for these two properties. Now I will ask for a new structure. The new structure is monoidal. What I want is to have a tensor product, an associativity constraint. Let me change the name, alpha. So the associativity constraint is telling me how to change parentheses when I have three things that are being tensor. I want to have a distinguished object in my category that it's the unit for this tensor product. And when I say the unit, I need to say it in the categorical way. So I will need to have two morphisms that are telling me that actually one tensor, any other object, is isomorphic to that object and doesn't matter in which side. So these are these two maps. And I will need some compatibility. So first of all, this will behave well with the like the addition. It will be bilinear, and also in objects, in morphisms. But the other thing is that I want to have two axioms. One, it's called the pentagon axiom, that it's telling you that this associativity is coherent. So the pentagon, you have the 5 ways that you have to put parentheses in 4 objects. And it's telling you that at the end doesn't matter which way you pick, basically. And then a triangle axiom that it's relating these two maps, the L and the R. So now this rigidity here is the one that will take care about the duals. So being rigid means that for every object X in C, we have left and right duals, and I will write only one of them, but there exists a dual. The dual is just another object in the category, but that's not enough to really describe what the dual in a category is. You need to have maps that are called evaluation. And this is very similar to the idea in vector spaces. So you have an evaluation map. And here we'll go to my unit, which in vector spaces or in RepG is the field. And I want to have a co-evaluation map here. And as usual, this is not enough. I want to have certain coherence, certain axioms, and these are called zigzag axioms. I'm doing some graphical calculus notation, but basically it's telling you that if you compose evaluation and co-evaluation, in certain ways you get the identity. And for example, when I was doing this other example, I started asking finite dimensional representations, and that's because otherwise we don't have a dual here in the categorical sense. You can do this, but you will never get the co-evaluation satisfying these things. For this to exist, the evaluation always exists, but for this other map to exist and be coherent, you need finite dimensional. So it's kind of, again, giving finite dimensional, and this is a property of this monoidal category, if it is or not. And now this here combines or look at abelian at monoidal at the same time. The unit of the monoidal category need to be a simple object in my category, in the abelian sense. All this here is telling me what a fusion category is. And if I drop semi-simple and I modify a little bit this is a finite tensor category. Now, I also want a braid. A braid is making my tensor product commutative in a coherent way, always. So I will have, and again, let me change this, I will call it sigma. I will have this natural family of natural isomorphisms plus 2 hexagon axioms. These hexagon axioms are basically the braid equation, or if you have in mind that braid equation, but it has more places because in principle you need to insert associativities that are non-trivial. If your category is strict and these are all trivial, then these are the braid equations. So it's telling you how this braid behaves when I put a tensor product in here or a tensor product in here. That's what it's telling us. And this braid was the flip, or one possible braid for rep G, not the only sometimes. It's the flip, for example. So we have the braided fusion category. There, the problem is that that braid, if you think about this braid 1 second, if we do this 2 times, of course, here this depends a little on the labels, but I will abuse of notation and say that I do the square of this, and here I need to put the labels that correspond, that are the correct labels. Sorry, and here it should be these. Then if you flip and flip again, you get the identity. So that braid is quite of the opposite of what I want for modular. That braid is very degenerate. So I want something opposite that it's non-degenerate, and I will tell you in a minute. Before that, the other thing that we need for modular categories is the existence of something called twists. And these are maps from every object to itself. And these maps need to, again, behave nicely with the tensor product. So this is not a tensor functor, let's say. It's related to this square of the braid. And this square of the braid, I call this the square of the braid, because now when you do this, you go from X tensor Y to X tensor Y again. This is something very important, and that's measuring the degeneracy of your braid. So when you have this, you can create something called the T matrix. That it's a diagonal matrix that basically has in the diagonal the numbers associated to this map when X is a simple. When X is a simple, you have a Schur's lemma, like in representation theory in this abelian context, and this will be just a number, a non-zero number. And we get a T matrix. And using the twist, we can also look at certain trace, and that will give us another matrix related to this that I will write now. This is a subcategory, and it's called the Muger or the symmetric center. I call it the Muger center. It's also called the symmetric center because it's measuring how far your category is from being symmetric. Symmetric means this, that always when you do the square of your braiding, you get the identity, that you squaring doesn't do anything. So is all the X in C such that this thing here are the identity for every Y in C. So this is kind of a centralizer, generalizing the idea or categorifying the idea of centralizer. So this is itself a symmetric category. And what we will ask for being non-degenerate, maybe I should change the color, for that we will ask that this is the category of vector space, finite dimensional vector spaces, as smallest as we can. So what we are saying is that the only object that it's transparent for the braiding is the unit and things generated by the unit. So that's, until here I say premodular, this is kind of a premodular structure, and here I say modular when I have all this. So let me give you some quick examples. So if you don't know what this is, it's okay. I will just mention for the people that know, but I will talk about this Hopf algebra example because this generalizes very nicely the idea of the group. So here we have a semi-simple finite dimensional Hopf algebra. And I will look again at the category of finite dimensional representations of H over C. So having a Hopf algebra means that I have an algebra structure, but also I have a coalgebra structure, and I have an antipode. So this coalgebra structure is, if you have a multiplication, you have something like this, that it's associative. Getting a coalgebra structure, it's switching, it's pointing the arrows in your diagrams in the opposite way. So here we have something from H to H, tensor H, that will be co-associative, and co-associativity is exactly switching the arrows. And the same for the unit and the co-unit. The co-unit is a map from H to the field, And this antipode is an anti-algebra map. For this to be here, a Hopf algebra, I need, of course, some compatibilities, and these two, for example, need to be algebra maps, plus some axioms that they need to satisfy. I will not write the axioms, but I wanted to mention this structure because not every algebra will a priori give you, or not the representations of every algebra will give you a priori this tensor category. What is magic about these Hopf algebras is that this extra structure let me create, or let me endow my category with the structure. So the tensor product will be given by the co-multiplication. So if I want to act by H in some tensor product, what I will do is I will act using this co-multiplication. And I'm abusing of notation. These don't need to be homogeneous vectors. Here you need to imagine that I have a sum of things, but basically this delta is partition, or it's splitting your H into pieces, and you can act with the first factors here and the second factor here. And here the unit will be again the field, and this is kind of the trivial action. Maybe I should be using the other color, but the trivial action, but now the trivial action is acting by the co-multiplication. So now any H can be taken to something in the field using this thing here. And duality, I will not say much about it, but it's given by the antipode and the inverse of the antipode, which in this case, because we're in the semi-simple case, they are equal. And there is even a condition on when this H is, or when this category is braided and comes from this algebra having a special name that is quasi-triangular. And it's related to solutions of Young-Baxter equations and something called an R matrix in your Hopf algebra, because Hopf algebras were also useful, and quantum groups were also useful for that, for finding solutions of Young-Baxter equations. And this is where this appears. There is also a condition for being modular. It's more technical, I won't say it, but the algebra in that case is called factorizable. There is some property that factors. So let me give you 2 or 3 other examples. And maybe let me say that here we can recover the previous example by looking at H, the group algebra. And the group algebra has a nice structure of Hopf algebra. The co-multiplication is just diagonal. This is 1, sorry. And the antipode is the inverse, because the antipode is playing this idea of an inverse. The problem is that I didn't write the property, the axioms, but it's kind of an inverse in some way for these elements in the Hopf algebra. So what I want to present now is a generalization of, or again, thinking about having a finite group. So this will be a finite group, and I want to construct a new fusion category. And what I will look is at finite dimensional vector spaces that are graded by my group G. So the objects are vector spaces that admit this grading, where these are subspaces, just labeled by the group elements, and they are finite dimensional complex vector spaces. Now, this has finite dimensional C vector spaces underlying. So I will keep all the things in mind that I already know for vector spaces. I just now need to have in account the grading. So what are the maps? Here are linear transformations that preserve the grading. So the component G is mapped into the component G. And the tensor product in this case will be kind of a convolution product. So what I will do is I will take all the things that when I tensor together, the labels multiply to G. And I will add all of them here. And that will give me the G component, or the degree G of the tensor product. The unit, we know that for vector spaces, the unit is the complex. It's just the field, or the one-dimensional vector space. So this will still be a one-dimensional vector space. But now I need to explain, because I have a grading, and these are subspaces. So most of my subspaces will be 0, and only one will be everything will be the one-dimensional thing. So I will say that it's concentrated in degree E. And E is the neutral element of my group. So basically what I'm saying is that the components in the grading of this will be 0 unless I'm in the E component, and in the E component I have the complex. And now you can ask me, okay, but why this E is the only important one? You could do the same thing with all the others, and that's true, and that are other very important objects. So the one-dimensional vector spaces concentrated in degree G for each G have a name. They are called delta G because basically you can write something like this to describe them. And E, and the unit is just delta E. And these objects are very nice for many reasons. One is that the tensor product is very simple. It's basically the multiplication table of the group. The dual, it's also very nice. It's just the inverse. So you are recovering the group structure, or in some way in this way. But also any object can be described as a sum of these objects. So these are simple objects because they are one-dimensional, so you cannot have any sub-objects that are not everything or 0. And you see our category is semi-simple. And then the only thing that I should be telling you to tell you the fusion structure at least is the associativity. I could give just the trivial associativity from vector spaces, but in this case I can also do something more fun. This is a one-dimensional vector space. At the end of the day, this is just this, and this is the same space. So what I have is a map from a simple to a simple to itself. So by Schur's lemma, this is just a multiple of the identity that I will call like this, just because it depends on these elements. It's non-zero because this is a, and here, sorry, I should write alpha because I will use A for something else. And the pentagon axiom that I mentioned before is a 3 cocycle condition on G. So actually I could decorate here with a 3 cocycle, and that also give me a new fusion category with a non-trivial associativity constraint. So another way to create, until here I only told you some fusion category. This can be endowed sometimes with a structure of a modular category. For that, first of all, the group need to be abelian because otherwise you don't have braidings on it, and because you want commutativity of the fusion rule, so otherwise you won't have it. And then you will need extra things to describe the braid, and actually it's related with some abelian cohomology, so there will be some quadratic form or some bicharacter involved, and for being modular, the category that bicharacter or that quadratic form need to be non-degenerate. So that's a source of modular categories. Other two sources that I will not describe in detail, but I want to mention are doubles. So if you start with a finite group and a cocycle, I told you that you can create this category, but in principle, this will not be modular. But you can also look at the double of your group, which is looking at the group algebra tensor, the functions of the group. This is an special Hopf algebra. And the representations of these is a modular category. And even if you twist this with a cocycle, and I will not explain how, but you can deform one of the structures with this, you still get modular. And one question would be, are these related? And the answer is yes, and I will tell you in the next slide how they are related. And we could do the same, so here I wrote 3 prime, because we could do the same with any Hopf algebra. There is a double construction, and the double of H, the representations is always modular. It's non-degenerate, which is strong. And then other big source and our main source of examples of modular categories are Lie algebras, are quantum groups. So if you start with the simple Lie algebra, you can look at the enveloping algebra, you can quantize. Here you will use some specific root of unities. and not always you will get modular. So there will be some restrictions. Maybe there are restrictions here, but. And then the next thing that we do is we take the representations. This sometimes is not finite. So what we will do is we will do some purification, looking at some tilting modules. We will eliminate some things, and this will be modular. Again, for some things, I need restrictions on L here, and I will not give the details, but this is our main source of examples, I would say. So now I got to one of the points that I wanted, and it's talking about how we can get new modular categories from things that we know. So here's where I want to describe constructions. So I will give you a sampler of constructions, and hopefully I will talk more in detail about two of them. So the first one is kind of a direct product. This Deligne product can be done in many settings. In particular, if you start with two modular categories, you can take something called the Deligne product that again is very much like a direct product, at least in the semi-simple case. Otherwise, it's much more complicated. And the nice thing is that you keep getting modular. So the simples here are just labeled by products of simples in each of the categories, or here maybe J, sorry. Simples here and simple here that give you all the simples, and you still get a modular category. Then the next construction is this Drinfeld center. So this is, remember I talked about Muger center, which was the symmetric center and was a subcategory of my category. This is an outside center. What I'm doing is I'm adding, or I'm looking at all the possible braids, that I will call half braids, that I can give to my objects. Half braid because they only satisfy one of these, one of these hexagons. So they only satisfy the braid equation in one of the sides, basically. And that's called the Drinfeld center. And if you start with a nice category that I call spherical, but this doesn't matter much, it's that I can take some traces, and the traces are nice, but don't think much about this. Then in this case, you get modular. This is always braided. This is always non-degenerate. This thing here is to get the twists. That's why I'm asking for this technical thing here, but don't think much about that, doesn't matter. And let me go back and tell you that here they were connected because this rep d omega g is the center, or in other words, can be said that it's the Drinfeld center of Beck g omega. Are two different ways to realize this, or two different ways to look at it. So the center is a very nice construction that we use. And then Muger and Bruguière, they studied independently at the same time the following case. You could start with something that it's braided. And you can look at the Muger center. And in this case, maybe the Muger center is not Beck. But again, this is a symmetric category. Deligne classifies symmetric categories. They always look like rep G, but they might have a different braiding. If I do have the flip as the braided, and in this case, we call them Tanakian. In that case, when we're in this specific case, what I can do is I can kill that by quotienting in some way. What we will be doing, it's called modularization in this specific setting and can be done more in general. And what we are doing is we are taking modules over some specific algebra, which algebra, the algebra of functions of this group G inside my category. And why this was important, because in this case, the algebra is commutative, and then everything works well, and you get a modular category. What it would be happen if this is non-commutative is that this will not be even fusion. You will have some problems with the home spaces. It will not be vector spaces per se. There will be some problems. But this is another way. And then Drinfeld, Jelaki, Ostrich, and Nijik generalize somehow this, and they say, okay, maybe it's not that all the Muger center is rep G. Maybe we have something super Tanakian, but let's pick the biggest, the maximal Tanakian subcategory, and let's do this. Let's do the same thing. Now we don't get a modular category. We get something called G crossed braided fusion category. And we take now the 0 piece of this. This has some nice grading. And this is modular if C was modular. So this is another way to construct. Then other construction that I was planning on talking about it, but I might skip if I don't have time. It's this relative tensor product. So it's related with this idea, but now we will not start with two modular categories in principle. We will start with something called braided fusion categories over epsilon or over some symmetric category. And what we will do is we will take, again, some Deligne product, but we will combine kind of taking this Deligne product and taking this core. And here this epsilon will be playing this role. So it's kind of a combination of the previous one, and the notation, it's this one. And this is a new construction of a fusion category, of a braided fusion category, or for modular category, depending on some other conditions. But it's a new source of categories that sometimes is related to other constructions. And this construction has some nice things. It's not that easy to compute sometimes explicitly, but it has some theoretical advantage because by some things, you know that, for example, certain properties of the category are preserved, or you know very easily how to compute some invariants, not all, from invariants here. So that's why this one is also nice. And the two that I will focus today are these joint projects with my colleagues. This is with Sui, Galindo, and Shenhan Wang, and this is the one with Deligne, Galindo, Rowell, and Ching Sang. And this gauging process was also studied in physics by Parsa Bonderson, Barkalish, Cheng, and Shenhan Wang. Sorry, I'm writing set and I should be writing Wang, sorry. So gauging is a very well-known procedure in physics to promote some global symmetry into local symmetries. And so what we will do is we will start with a modular category and an action of a group in my category. This notation here is a group, is a categorical action, and I will tell you later a little bit of what this is. And what this let me do is construct a new modular category. But the process is complicated, I think, appears in different fields, so I will mention that in the next slide. And the other procedure is Zesting. It doesn't need to start with modular category. I'm writing here modular because I was talking about constructing modular categories. It's more general. You will start with some category that admits a grading. And I will say a little bit more about this in the next slides, but what it means is that I have this decomposition of my categories, the direct sum, labeled by some group. These are full abelian subcategories of this category. And there is a nice coherence between the tensor product and these components. And in certain specific settings, when I pick the group well, and when I have some nice relation that is kind of technical, in that case, when I zest, I get again a modular category. Zesting is related to deforming some of the structures, and I will tell you how. So this is modular again.
So, Julia, in this example, C could be fairly general to start with. Does it have to be braided?
In this one, you can start with non-braided, but you will get something or at least in how we do it, we will only deform that. We will only deform the associativity and the tensor product. So if you want to get something braided by zesting, you should start with something braided, and you can like deform the braiding too.
Oh, okay. So all the structures get deformed, I see.
Yeah, everything gets deformed. And one thing is that you don't necessarily start with modular and get modular. You can get pre-modular again, because that's what we will be doing. We will be deforming, but being modular is a property. It's just checking if some center is trivial or not. So we can deform something that it's modular into something symmetric, in which the center is opposite. So that's kind of fun too. In this specific setting that I didn't explain, but it's with an extra condition, we get modular. We can ensure that we get modular. And in many other cases, we can start with something braided here and get still modular or not. So that's kind of fun, that we have some liberty.
Okay, thanks.
Or freedom. No, thank you for the question. So I will start first with gauging, and I will give like an idea of it. So I will start with my modular category, and this MTC stands for modular tensor category, that maybe I should say before, but I will start with this modular category and with this categorical action. What it is a categorical action? It's a tensor functor from this category and I will go to the autoequivalencies of my category, and I will look at tensor autoequivalencies. So these are special, so these are functors from C to C that are equivalencies, but I also want them to behave well with the tensor structure. So I have more structure on this. And actually this T is a tensor functor itself. So it's sending C to some T sub G that goes from C to C, and it's itself a tensor functor. So here, this secretly, I'm writing 2 times tensor functor, and that encodes a lot of information that I'm not giving there, but it's a lot of information. It's like a lot of diagrams that commute, or a couple of diagrams that commute. So this is the input. This is my input. What is gauging is a 2-step process. As I was saying before, this was well known in physics. And actually, it's also, I think, related to some process in other fields, like, for example, in VOAs or in conformal field theory, this is related to orbifold, or maybe it's the same as orbifold. The thing is that we don't know if every modular category is come from VOA or CFT, so we still wrote it in a different way and has its advantage to study some of the things in modular categories. So this is a 2-step process. The first step, we will do something called a G extension. A G extension, I think of Nikshik and Ostrich. So there is this nice paper about fusion categories and homotopy theory. And the idea is that you start with a fusion category and you want to get a new one, which is a bigger category, and it's given in this way that I was mentioning before. This will be a billion categories. The trivial component of this should be the one that I started with, this one. And each of them, for being an extension, I need all of them to be non-trivial, all the components being non-trivial. And what's this grading? I was telling you there should be a compatibility between this and the tensor product. I want this to be fusion. So it's that when I tensor, I get CGH. Now, if I started here with modular, starting here with modular gives me more structure on the output. This extension is something called a G cross braided fusion category. And what this is, first of all, it has an action. It's endowed with a G action, similar to this thing here. It's the same thing. And instead of being braided, it's G cross braided. So now if I want to go from X to Y, I will not land again in Y tensor X as before. If X is in the component G, here I will be acting in Y by G. And I will get some similar hexagons, but I have this deformation. The important piece here is that I didn't get a modular category because it's not even braided in principle, but I did get an action. So now what I will do in step 2 is use this action again to construct. So this is a construction of fusion and braided categories. And here is another construction in fusion categories that might be also similar to constructions in different fields, that it's taking fixed points. It's a category of fixed point for an action. So what I will say is I will use this action now, and I will take the category of fixed points. And that will be my second step. So here, the G extension, I call it, sorry for the messy slide, I call it CXG. Now I will take that the gauge, the output, is the output of the second step applied to the output of the first step. So I have this, and I will take the fixed points by G. It's a category of fixed point. It's just a notation. This notation is not very beautiful. I apologize, but the idea is this. We first do the G extension a la ENO. We get a G cross category. So we have a categorical action, and now we take the fixed points under that action, and that's modular. Why is modular? For many reasons, or for two reasons. One is because the input was a modular category, so this trivial component was modular. And because each component was non-trivial and the trivial component was modular, when you take fixed point, you get something modular. This is a result of Drinfeld-Jelakin-Nikshik-Ostrich.
Julia, can I ask you a question about this? So
yes.
if C is, for example, the purification of a category of representations for a quantum group at a root of unity, so is there a G here which acts on this? So is there do you have an example of this gauging?
Yes.
Okay.
So here is an example, and it's one of these. I didn't grow the bar here, but yeah, it's one of these quantum group examples. So these come from SL3 with some Q, and this has a set to symmetry. This is kind of the simple objects. And you will see the set to symmetry I will reflect here. So these are fixed here, but they change here. That is set to symmetry. So I'm at this level here. I'm doing this action, and I'm just describing in objects. But this upgrades to a categorical action. So I'm here telling you just at kind of a group level what I'm doing, but this upgrade to a categorical action. So the first step will be taking this set to extension. And I'm not describing all the things, but the trivial component, as I mentioned, is the original category. So I only have an extra component. And in this case, the extra component gives me two new objects. And now I need to take the fixed points. It will be, so I will be taking again set to fixed points of this here. And it's interesting because when you take these fixed points, can happen two things. Or the object that you are looking splits in two if it's fixed under this action, or if this object goes to another, it gets combined. It's kind of crazy what happens. And what we obtain is a new modular category with 12 objects now. We started with something here with 10. So these have 10 simples when I started with, and now here I have 12 simples. And this is a coincidence. It's not like you always preserve when you take fixed point. This was just a coincidence. And it was not super easy to do. And something that was very important was to look at something called Frobenius-Schur indicators. The fusion rules of these fixed points, so of these steps, have been studied by Bursio and Natale, but it's non-trivial. It takes a lot of looking into some projective representations and things like this. And sometimes to be able to finish computing things, you need to look into more structure in the fusion category that you start with. And you get a new, when we did this paper, this was one of the nice outputs because we didn't know this category before, this rank 12 category. So it was kind of something exciting to get.
So this category is brand new, like in Nature, nobody saw this category before this output.
We didn't saw it before this thing, yes. Yeah. But then people start looking how they can find it from some other examples, basically. That's kind of the game. How can you construct it from some other things that you know? So some remarks about this construction. We know the dimension. There is a notion of dimension. It's called Frobenius-Perron dimension. There is another that it's called quantum dimension. But what I want to say is there is a notion of dimension. And what happens is that this gauging changes the dimension of the original category by multiplying it by the square of the order of the group. Each steps add the square of the order of the group. So you get a bigger category. There is something called the width group, width equivalence. A lot of the time we want to understand fusion categories, modular categories, tensor categories, and equivalence of tensor categories is very strong. So we studied something that it's called width equivalence. I will not explain, but one of the things is that it's preserved under this operation. So you don't get something out of the width class. And the other thing is that there is another nice, and if you are familiar with conformal field theories or vertex operator algebra, this also appears. This is called the central charge of the category of the VOA of the. It's preserved by this operation also, by gauging. So it doesn't change central charge, for example. One thing that I can say about the width class, if you started with the center of a category, with the Drinfeld center, width class is preserved. So you will still be a center of a new category via gauging. So if you are a center, you don't change that nature, for example. That's something why it's important, the width class. One comment about existence, because I told you how to do it, but you cannot always do it. Not always. You cannot always perform gauging, and it's because there are obstructions to step one. ENO theory has some obstructions. And these are cohomology obstructions. I will not say much about this, but basically what you need to do is you start with this categorical action and you want to upgrade it to some upper level, like a higher categorical. So these are groupoids. You want to go to a 2 groupoid, and to upgrade it, you need to pay some obstructions to vanish. So it's not always possible. So let me tell you very quickly about Zesting, because I know I'm running out of time. So a little bit about the history and motivation. We started seeing this Zesting, we call it Zesting, appear in nature somehow. A lot of years ago, in 2012, in an AIM workshop, we studied classification of modular categories of a very specific dimension, 36. And we found a fusion ring, so the fusion rules, how to tensor things, that look very similar, but not quite the same as this one that I just showed you, SU3 level 3, the one coming from SL3. And we saw that we can get it by twisting the tensor product by something called an invertible. Invertible means that when you do X tensor X dual, you get the unit. Because they are invertible in some sense, you get, so that's why. So we recognize that we can do that and find this new one out of this one by doing this thing. And that was the first time that we called something Zesting, or I don't remember if we put the name, but that was the first time that we saw this Zesting. Then a couple of years later, this we started in 2012, but it was published later. So in 2016, we were studying something called supermodular categories. Instead of the Muger center, the symmetric center to be vector space, you have that it's super vector spaces. And we wanted to know if you can always embed it in a modular category in a minimal way, meaning that this modular category has twice the dimension of your original supermodular category. This is comes from physics. There is something called the 16-fold way for supervec, and it's true. And what it was proved is that if there is one, there exists 16 of them. This is work of many people. And actually nowadays, David Reuter and Theo Johnson-Frey proved that it's true that it always exists one, at least when you have, that there exists always one. So we know that there are always 16 of them. And what was interesting that we studied some very specific example, again, coming from quantum groups. And we saw that we have two families of, or two important closures, and we were able to get 8 and 8 here via Zesting. So we got the 16, but came in 2 families of Zestings. And we know that these are very different because they have different number of simples. And one spoiler alert, Zesting preserved number of simples, so we couldn't get from one to the other. The other important way in which Zesting appears was categorifying things. Grossman and Izumi in 2018 gave us modular data, which are these S and T matrices, and we wanted to know if there are modular categories that have this modular data. And in 2019, Bonderson, Rowell, and Wang showed that it can be done using this Zesting construction and also gauging. And fusion rings, Liu, Shenwei Liu, Sebastian Palcu, and Ren, they studied some fusion rings, and they were able to categorify them using Zesting. Because that's another question. You have all these tensor products, they come from a fusion categories. Are there associativity constraints that satisfy that? So let me tell you very quickly what we did. We axiomatized this and we constructed an abstraction theory. So we start with a premodular category that it's graded in this way. So maybe, yeah. And what we do to test fusion rules. So we start with an associativity constraint and with a tensor product, and we will give you a new one. We start with a braiding, and we will give you a new one, and we start with a twist, and we will give you a new one. And the output will be this new, maybe I shouldn't write this, premodular category. So premodular category. Again, will be G graded, sorry, a premodular category. So how we do this? As I mentioned, I will start with a braided fusion category. This is braided fusion category, and I will assume for now that it's strict, so associativity is trivial. How I change the fusion rules? I will do it just by twisting them by an invertible object. This will be an invertible object that lives in my trivial component and depends only on the grading, in which my objects here live. So one is in A, the other is in B. This is an invertible object. How I change the associativity? What I will do here, I will preserve it, and here I will change it using some map that I will just abuse the notation and call AB lambda again. And this is actually a cocycle, and it will be, I will ask it to be normalized. You see that we have a 2 cocycle condition. So we want to do something similar with the braid. Let me just say what I'm doing very quickly. In the part of the objects that I already know how to braid, that are these 2, I will just use my braid, my usual braid. And here I will introduce some nice isomorphism between these objects. And if the lambda before was trivial, this will be kind of a bicharacter. So here I have a 2 cocycles. Here I have this bicharacter, and the twist, I will just change it, by a phase, by a multiple. I will not do anything very crazy. This multiple will only be a non-zero element depending on where my object is in the grading. So XA lives in CA. For this to really work, for this to give you a new modular or a new premodular category, associativity, braided, and twist, you need to satisfy a lot of abstractions. So there are a lot of abstractions. Maybe let me say here that we have abstractions in each step. And I know that I'm on time, so I will finish now very quickly. So I just wanted to say that we also assessed this SU3 level 3. And when we assessed, we got the new rank 10 CUNYRT example from 2014. This is the 2014 example. And you can see that the fusion graphs looks very different. So the fusion rules here were like this, and here we got very, very different fusion rules. And just to say some remarks about Zesting, why we like it, modular data, the S and T matrices and other invariants are very easy to compute, very concrete, and this is very hard usually. That's why this is a very nice thing. The braid representation associated to a modular category that I didn't talk about that, but it's also easy to compute. And if it's finite in your original category, it's finite here. Linked knot invariant, this was done by our RU student with Colin Deligne and Sang Kim, who is now in USC doing a PhD, and myself. These are also very nice to compute. S and T are some knots and link invariants, but we generalize these, but there are abstractions. And this comes from a problem with extension theory. This Zesting is a very particular case of ENO extension theory, but that it's very easy to compute, while extension theory is usually hard. So I will skip the pros and cons. And thank you for your attention. And I'm sorry that I went over time.
Thank you very much. Just thank Julia for that nice talk. Questions for Julio? So in this SU3 example of at level 3, how general is this? Could you do this Zesting or gauging? Does it work for other quantum groups?
Yes, it works. And this Zesting is a very, very nice case of Zesting. This is called cyclic Zesting because actually we are Zesting by certain invertibles that are set 3. So this made our life very easy on how to Zest, but you can do more general Zesting. And one of the things that it's nice about Zesting, depending what you do, I wrote it as a con, but maybe it's a pro, it changed, for example, the central charge. So for example, when we were doing this history here that I wrote, these were also coming from quantum groups, and we were able to give a very concrete way to Zest it. This was for super Tanakian, so when you have a super Beck instead of a Beck, but we have very concrete formulas, and we are actually working on doing a more systematic. I think Cesar Galindo, with one of his master students, has some even code to test some of the type A, maybe quantum groups. But you can do it in many cases. The important thing is that you, not exactly, but if you want to do something fun here with the fusion rules, you need to have invertibles. And a lot of these quantum groups categories don't have. So maybe that might make this part a little trivial, but then you can do fun things here sometimes.
I see. Thanks.
Thank you for the question.
Other questions for Julio? Okay, let's thank her again.
Thank you. Thank you for the patience. Sorry, I went over time.
No, it was great. I'll interrupt the recording.